Hi everyone, welcome back. So today we are going to continue our discussion of waveguides. So this is part 2 of lecture 22, where we will introduce finite element methods. So in the last lecture, we looked at calculus of variations to find the eigenvalues and eigenfunctions of a waveguide problem. And we saw that basically you have this expression, which is f of psi equal to integral over S gradient of psi dot gradient psi ds divided by surface integral psi square ds, right? And we said that this function evaluates to kc square, or this functional evaluates to kc square when psi is a wave function, right? Okay, so I should say when psi is a wave function and f of psi is minimum. So you have this functional f of psi. When this functional is minimized, that the argument that minimizes the functional is a wave function, or I should say is a eigenfunction of the wave equation, and the eigenvalue is kc square, right? So then we said that, okay, then the way to solve for the wave for the eigenfunctions is to minimize this functional, and that's what we'll do today using a numerical technique called finite element analysis. Okay, so finite element method is really divided into two camps. So one is variational approach, which we'll discuss today, which is sometimes called the Rayleigh-Ritz procedure, or the Ritz procedure, or the Ritz method. And the other one is using differential equations, which we'll discuss at the end briefly, which is the more traditional finite element method. And this is called Galerkin's method. And we'll discuss that as well. Okay, so what's the idea here, right? So you have this functional, and we want to minimize this functional in the space of all functions psi, right? So how do we do that numerically? So to do that numerically, we start by discretizing. So since we're doing waveguide problems, we'll discuss this waveguide problem as an example of a variational Ritz procedure. So we discretize the 2D geometry into a triangular mesh. Okay, and this is exactly what is happening when you use a wave port. Right? So if I apply a big wave port like this, right, and I have, I don't know, it could be a microstrip line, which is PEC like that, and then you have PEC out here. Then there is some 2D geometry associated with this wave port, right? That's all of the material that's touching the wave port that provides a 2D geometry. So HFSS is trying to find if this was an infinitely large waveguide, what kind of mode would propagate? And to solve that problem, it uses the Ritz procedure, okay, which we'll look at today. Okay, so given an arbitrary geometry for a waveguide, so let's say this is PEC waveguide, it discretizes this geometry into triangles, right, which is the mesh generation part of it. So we won't talk about how the mesh is generated. So let's assume you have some kind of mesh. Maybe it's something like this. I'm just drawing a random mesh, but there is a whole procedure of how to generate the ideal mesh and so on and so forth, which we won't discuss here. But let's assume it's some kind of a triangular mesh like that. Okay, so this is the mesh generation. Okay, so once the mesh is generated, then each triangle in this mesh, we'll call it an element labeled E, has 3 nodes labeled J. Okay, so I have a triangle of this mesh element. This is a single mesh element. I'll call this E, and this obviously has 3 nodes, J equal to 1, J equal to 2, and J equal to 3, right? So for example, this is one of the mesh elements, right? So this has 3 nodes, and some of the nodes, of course, are shared between different mesh elements. So most of the nodes are shared, right? So that's what we're labeling things as, okay? Okay, so I have this mesh element, and now my psi, which is the unknown uh, modal distribution over x and y, is discretized into a set of unknowns at each node of the mesh. Okay. So of course, in reality, my psi is sort of unknown everywhere over this surface. But I approximate it as if I only have unknown quantities at these points, at all the nodes of the mesh. So at all of these nodes, my psi is unknown. And I assume that if I know the value of psi at all of these nodes, then I can find the value of psi everywhere else. Okay, so I'm just making this a triangular mesh. That's the assumption. So I only treat the unknowns as points on a grid or on the nodes, and I try to reconstruct, or I assume that from these nodes I can create I can interpolate the value of psi everywhere else. Okay, so what kind of interpolation to use? It's for example, if I know the value of these 3 nodes, then I can interpolate from these values the value of psi everywhere here. That's obviously an approximation, and that's the finite element approximation. Okay, so what kind of interpolation to use? So the most standard interpolation is a linear interpolation. Okay, so how does this work? So first we'll draw the figure, and then we'll try to understand what it means. So let's say I have a triangle like this, right? So this is 1, 2, 3. And at each node I have some value. So let's just assume it's scalar. So at this node, the value may be 3. It's some value for the psi. And then at this node, the value may be 2. Right? So I'm drawing the triangle in the xy plane, let's assume. And then the value at each point, maybe here it's 10. Right? So to interpolate the value of, the value of this function at all points of this triangle, what I will do is essentially just connect these 3 points. Okay, and now essentially I have another triangle which is sort of elevated from this xy plane, and I assume that this triangle essentially is the value of this function at all points inside this domain. So this is my domain, right? And this is the interpolation, a linear interpolation, right? Okay, so hopefully that makes sense, and how you can interpolate the function given that you know the value of the function at 3 points of a triangle. Okay, so mathematically, what does it look like? Mathematically, this linear interpolation looks like this. So psi, which is the value of psi at all points x comma y, is given by summation j equal to 1 to 3 nje x comma y psi je. Okay, JE is value at the nodes, right? So this is what we solve for at the end. And then once you have this, these are your interpolating functions. Okay, so let's take a look at them. So maybe we can do it in a new page. So I have the same triangle, let's say. Let me draw that again. Okay, so I have this triangle. So actually move this down a little bit. Okay, and I also want to make copies of it. Okay. All right, so I have 1, 2, 3, same triangle. Right? And then I have a value here, which was 3. Right? The value at this node, I said was 2. And the value at node 3 was 10. No, at node 3 it was 2, and at node 2 it was 10. Right? So let's stick to the same numbers. So at node 2, maybe it was 10, and at node 2 it was 2. Right, so to interpolate these values, what you can do is you can rely on linear interpolation functions that look like this. So let me actually just draw the functions rather than drawing these, and then we'll come back to this later. So what do these interpolation functions look like, right? So let's say I take a point just that's 1 unit above, or 1 unit in z, and then from this point I draw straight lines to the opposite ends. Okay, so from here it would go there, and there. And then from here it would go here and here. Okay, so now the interpolation function looks something like this. That's one plane. This is the other plane. And this is the other plane. Okay, so this is nothing but N1E x comma y. This is N2E of x comma y. This is N3E of x comma y. Okay, so what we're doing in this equation here, so let me zoom out a little bit, maybe a little bit more. So what we're doing in this equation here is that we take these 3 interpolation functions, which are nothing but these triangles, right? This one, and this one. And we scale them up by the value of the node, right? So if this value was 3, then this triangle, this node of this triangle will be moved up to a value 3. So then the triangle would actually look like this, right? Then that will become this triangle. This node up is moved up by a value 10, and this node is moved up by a value to a value 2. Right? So then you have these 3 different planes. And then when you add those 3 planes up, you get exactly this, right? Maybe that's not obvious to see, but that is indeed the case, right? Because at this node, I only have contribution from the value at this node. So when this goes up to a value 3. There, this goes up to a value 10, which is this one. And this goes up to a value 2, which is this one. And of course, you have 3 different triangles, which are all gradients essentially, or constant gradient surfaces. When you add them up, you end up with another constant gradient surface, which is this surface. And so that's how you do a linear interpolation. So understanding what this function is doing is probably the most important part. Okay, and this linear interpolation has many nice implications. We'll see later. One, of course, implication is that taking the gradient of this is easy because gradient of a linear interpolation function is a constant, right? And if you go back to this equation, you see that we do indeed take gradients, and that will show up in a few seconds, in a few minutes. Okay? So hopefully now it makes sense intuitively what these three functions are and what exactly they're doing. So let me actually move this up a little bit. Okay. So the rest of it is now computation, right? So another thing to keep in mind is that at this edge, the contribution only comes from this node and this node. Right? Similarly, at this edge, there is only contribution from this node and this node, because this node goes down to 0 by the time you get to that edge, which means that the value at this edge only depends on these two functions. Since it doesn't depend on this, since this edge is shared by other triangles as well in this mesh, its value doesn't depend on the value at this node and another node in another triangle, right? So it maintains continuity. Since it doesn't depend on the value of these two nodes, it only depends on these two. This function is continuous across mesh elements, okay, just because of the way we've chosen the basis or chosen these triangles. Okay, so based on that, so this NJE is, so what is the NJE? What is the formulation, right? What does it actually look like? What function gives you this kind of triangle? You can pretty easily show, which we're not going to do here. I'll just give you the final result, that this function is essentially this BJEX plus CJEY. Okay, we'll see what AJ, BJ, and CJ are. They're also functions of X and Y, but essentially that's what NJE is. Okay, where J equal to 1, 2, 3. So what are these A1, B1, C1, A2, B2, C2, A3, B3, C3? So A1E is X2E, Y3E minus Y2E, X3E. B1E is Y2E minus Y3E. C1E is X3E minus X2E. Okay? And similarly, you can get A2E, A3E, B2E, B3E, C2E, C3E by cycling through the parameters through indices, let me say. Okay, so essentially A2 will be 3, 1, 2 becomes 3, 3 becomes 1, 2 becomes 3, 3 becomes 1. So similarly, B becomes 2, this becomes 3, this becomes 1. So 2, 1, 3, and so on. Okay, and this is 3, 2 plus 2 is 1, 3 plus 2 is 2, and again 1, 2, and so on. Okay, so essentially n is a function of x and y. Okay, so given a triangle in some coordinate system, you know what the xy values are at the nodes, and then from those you can find what the value of n is at all points of these nodes. Okay, and this triangle here is the area of the triangle. So essentially all of it scales by the area of the triangle. Okay, that's one of the nice properties of these functions as well, is area of triangle, which is nothing but 1/2 B 1EC2E minus B2E C1E. And that also you can show. So these are all well-known results, nothing new. Okay. So psi of x comma y essentially becomes summation of all the elements psi e x comma y. Yeah, that's nothing but summation over all the elements and summation over each of the nodes with the interpolation functions. Okay, so note that these are the only unknowns. So I should say these are unknowns, and this is entirely determined by the mesh. Right? So once you have the mesh geometry, your interpolation functions are determined. So the only unknowns that you need to solve for now are this psi term, right? Which is nice because now you have a discrete number of psis that you need to find. So this again goes back to the idea of taking equations in calculus and converting them to matrix equations. That's the whole philosophy behind numerical techniques, right? Okay, so let's actually move forward. So once you have the mesh, how do you actually find these unknowns, right? That's what we want to do. So we revisit our equation, f of psi, s gradient sigma e equal to 1 to n, psi e of x comma y dot gradient sigma e equal to 1 to n, psi e x comma y ds, all divided by surface integral summation e equal to 1 to n, psi e x comma y whole square ds, right? Okay, so we want to show that taking the derivative of this with respect to the basis function, the unknown quantity, psi je, setting this to 0 gives psi je so this is the vector of elements or the vector of nodal quantities, which eventually which closely approximates the eigenfunction, right? That satisfies the wave equation. So earlier we said that, okay, you have to take the derivative of f with respect to psi, right, which is the function. So derivative of the functional with respect to the function. But now we are saying that since we have discretized it into a set of unknown quantities psi je, it's essentially like saying that what is the vector? So this is a vector, right? Because it's a function of, I mean, basically you have psi 1. So if I write down psi je, what does it look like? Right, so psi vector is psi je, which is nothing but first element, first value, first element, second value, first element, third value, and then you have the second element, first value, second element, second value, and so on. So this big vector of unknown quantities is, what's the dimensionality? So you have 3n cross 1. Right? That's the size of this vector. Because you have n mesh elements, and for each mesh element you have 3 nodes. Now, of course, many of the nodes are shared, so the final psi is actually not this, but the psi that we are dealing with so far is this. And several of the mesh elements of several of these quantities in this vector are repeated because they are shared nodes. Right? But for now, let's just treat it as completely unknown. We're ignoring the part that the nodes are shared. So that's the vector. So now we are kind of optimizing or minimizing this f. Instead of over function space, we are minimizing with respect to vector space. Right? So you have a bunch of vectors that all give you different functional values. Because you get the vector, you put it into this basis expansion or this interpolation expansion. That gives you the final psi. And instead of minimizing over the unknown psi quantity, now we are minimizing over this vector space of this psi je. So that's the idea. Okay, so trying to do that, is the next part. So let me erase this because now you understand where this vector thing is coming from. Okay. Vector of nodal quantity closely approximates the eigenfunction. Okay, so solving this equation essentially will give you a matrix equation. So we'll do the derivation. It's a bit of a long derivation. So we'll do it once we write down the final result. But I just wanted to write the final result. That reduces, so that equation up there reduces to this equation. C square, B tilde, psi tilde. Okay. So this is the finite element equation, let me say. Okay, and where this A is a matrix called the stiffness matrix. Because finite element comes from structural mechanics, and that's why you have these kind of structural mechanical terms. B is called the mass matrix. Okay? And A tilde is given by Ij. So this stiffness, we'll discuss what A tilde and B tilde are, but A tilde is basically a block diagonal matrix where its elements are given by BIE, BJE, CIE, CJE, and B tilde Ij is given by triangle, which is the area of the triangle, 1 plus delta Ij. Okay, and this is the Kronecker delta function. Kronecker delta. So when I equal to j, it's equal to 1. When I not equal to j, it's equal to 0. Okay, so we'll derive these results, but essentially, what is this matrix equation telling you? Right, this is a generalized eigenvalue problem because this matrix is known, this matrix is known, it's entirely determined by the mesh. This is an unknown quantity, this is an unknown quantity. The eigenvalue, of course, is also unknown. And this is essentially is nothing but what is called a generalized eigenvalue problem. Right? And these kind of problems have been solved before, and there are many techniques to solve them once you get to this stage. So that's kind of beyond the scope of this class. Once you have this, you can put it into MATLAB or Python or any kinds of matrix solvers and get the final result. Okay, but these matrices are still, so this is a 3n by 3n matrix. This is also 3n by 3n. And these are block diagonal matrices. And we'll see why they are block diagonal during the derivation. But we still need to do one more step, which is that psi tilde, the way we have it now, once you solve this, has many repeated elements because of the nodes that are shared. Okay, so we need to reduce this. Reduce this to approximately n vector, n by 1 vector, right? So from 3n by 1 to n by 1. It's not exactly n by 1 because not all the nodes are shared. You have some nodes that are not shared, right? So the nodes that are on the edge. So maybe I shouldn't even say this, right? To remove repeated nodes. Okay, and this is done by something called the connection matrix. So psi tilde is given by connection matrix C times psi. These are obviously vectors. Right, so psi tilde was the vector you solve for, or you would solve for in this equation. But instead of solving directly for this, we can make it a little bit simpler, this connection matrix, since we know what the connection matrix is for a given mesh. You can get this quantity psi, which is a reduced form of psi tilde. Okay, so if I make this substitution into the equation above, then your final finite element problem, eigenvalue problem, is A psi equal to kc square B vector psi. Okay, where A is nothing but C transpose A tilde C. That's your connection matrix. And B is nothing but C transpose B tilde B, B tilde C. And then this is kind of trivial, obviously. If you go back in here, you can substitute psi tilde from this equation, and that will give you C psi. You have a C psi here. You multiply with psi. You multiply with C transpose on both sides, and that essentially reduces to A equal to kc square B. A psi, I should say A psi equal to kc square B psi. Okay, and that's exactly what we have here. So this is really the final finite element formulation. So this is the generalized eigenvalue problem. So you only need to solve for this. You don't need to solve for the previous one because that's a larger problem. Right? It's not the reduced form. So it has many uh, redundant vector values, vector element values. So this is a generalized eigenvalue problem. So the goal today is to kind of reach to this point. Once you reach to this point, then you can obviously solve it using many different solvers. Okay, so now we actually want to see the proof and how do you actually get here, right? And I like to do the proofs in the lecture notes just because I don't like to leave things hanging. So let's do that next. Okay. So computing df psi over d psi, right? That's what we want to establish, where psi now is a vector. Okay, so we know f of psi, which is the functional, it has a numerator and a denominator, right? So we'll do them separately. So I have gradient psi dot gradient psi ds, which is nothing but surface integral gradient of summation over e, which goes from 1 to n, summation over j, which goes from 1 to 3, psi je, nje, x comma y. That's the expansion we just used, dotted with same thing, summation over e, summation over j, psi je, nje, x comma y. Okay. Okay. So where my n of ne, psi e, maybe I should clarify one thing. Maybe I can call this like fancy n or block n. So I'm talking about this block n. So I can write this n of psi, this block n of psi, which is what I have out here, as a summation over each element. Right? So the left-hand side is over the whole space, and I can write it as summation over each element. So this is capital N. So what I'm doing essentially is pulling this summation up. And that's fine because the gradient is only over this term. Right? So I can either take the gradient over the whole space after summing it up or take individual gradients. And that's what I'm doing here. Okay. So if we do that, then what happens? Then we only have to treat this term. We don't have to treat the full summation right now. right? So summation over every, or this numerator quantity of this functional over an element is now summation over every element rather than summation over the whole aperture of the waveguide. Sigma j, je, can pull the gradient in now, and the gradient only applies on this nj quantity because only that's a function of x and y. So dotted with summation over, let's say this summation is over e, and ie, ds. And now my ds is only over a single element. Okay. And remember that the way we chose nj and ni is for them to have constant gradients, right? Or constants. Okay. So because they are constants, when I integrate, I essentially only have, I can pull them out of the integral, right? Since it's the constant, the integral doesn't really, this is no longer a function of x and y once I take the gradient, right? So then when I integrate, I can basically pull this outside the integral. Okay, and that's the big advantage of using these linear interpolation functions. Okay, implies log n psi e is now summation over I, summation over j, psi ie, psi je, gradient nie dot gradient nje times surface integral of the triangle ds. But this is nothing but the triangle, right? That's the area of the triangle. Okay, so maybe I should put a subscript. Should say this is the, hopefully you get it from the context what the different triangles are. But this is basically area of the triangle, which we already know, which we call this capital triangle of E. Okay? Okay. Now we need to also compute the gradient over Ni dot Nj. So this is not a very difficult computation. We have the function Ni and J, E as a function of x, y, and all of those constants, which are also functions of x and y. So you can essentially take the gradients in Cartesian coordinates, and you can show after some algebra that is nothing but 1 over 4 triangle E squared, which is the area squared, times BIE, BJE, plus CIE, CJE. So this is after some algebra, which is not very hard to do. Which means that now I have this term for this term, triangle for this term. So basically that triangle and this square cancel, right? And I'm left with block NE psi e. So the numerator of the functional for every element psi is nothing but summation over I, summation over j, psi ie, psi je, aij, e. Okay, where aij is the same stiffness matrix element that we discussed earlier. Now we've derived it. BIE, BJE, plus CIE, CJE. Okay, because the triangle squared and the other triangle got cancelled, right? This one went away. Okay. So I can write this whole thing as an E psi E as a vector now, element vector psi times matrix A times another vector, same vector, right? Transpose times that. And that's exactly what's going on here. So if you write this, for every I, if you write this as, so this is a 3 by 1 vector. This is not 3n by 1. This is 3 by 1. This is also 3 by 1. So 3 by 1 times 3 by 3 is 3 by 1 vector. And that times 1 by 3 is a scalar. And you get the same scalar if you do this kind of summation, double summation, right? So this is just a representation of this. They're both identical. So if you're familiar with some linear algebra notation, then that's fairly easy to see this. Okay, so we have a numerator term. Next, we need to do the denominator, which I'll call E psi E, which is integral over a single triangle. Now again, this is for a single element. ds. So I've already pulled out the summation over all the elements, and I'm just considering a single element, similar to how we did it for the numerator. And this is triangle E, summation over I, psi IE, and I, times summation over J, psi JE and J, ds. Right? Okay. And once again, you can pull the summations out. Summation I, summation J, psi IE, psi JE. These are not functions of X and Y. And you're left with just area integral Ni and J ds. And they're both functions of X and Y. Okay, so this integral can also be computed analytically because indeed you have expressions for X, Ni and J in terms of X and Y, and the integral is also over X and Y. So this also I'll skip just because it's kind of just long algebra. And this turns out to be area of the triangle divided by 6 when I is equal to J, and area of the triangle divided by 12 when I is not equal to J. And of course, another way to write this is the area of the triangle divided by 12 times 1 plus Kronecker delta ij. Because when I is equal to j, this becomes 1, and then 1 plus 1 is 2, and that becomes lambda delta over 6. And when I is not equal to j, this is 0, and you get the delta over 12. So this is a succinct notation. Okay? All right. So you can compute this yourself for different values of I and j. So pick 1, 1, and you'll see you'll get this. Pick 1, 2, take all combinations and do it manually over a long calculation. And you'll see that you can convince yourself with some algebra that this is true. Okay, so that's not easy, not very hard to do. So implies this now is summation I, summation j, psi IE, psi JE, BIJE, where my BIJ is the mass matrix, and it is given by exactly this, which we saw earlier. So now we've kind of derived that as well. Okay. And again, I can write this in vector form, or vector matrix form. Psi E transpose BE psi E. So I'm kind of switching this E from subscript to superscript, but hopefully from the context you can tell which one it is. Okay, so now I can go back to my F psi as a vector now, because now the vector is the only unknown. It is in this form, right? Divided by psi transpose B vector psi, right? Where psi is, maybe I should specify this. So this is for every element, we had this to be true, right? Is for each element. But now what we can do is that if I write psi as the stacked version of psi E, right? So psi is 3 by 1 vector for ijk, or 1, 2, 3 for j equal to 1, 2, 3. And psi vector is the stacked version. So this is a 3n by 1 vector, what we saw earlier, right? And I can write A and B are the block diagonal forms of AE and BE. And then we have this equation, f of psi, full vector. This is the 3n by 1 vector. 3n by 1 is equal to this form. Okay. So now the A and B matrices are 3n by 3n, and your psi vector is your 3n by 1 vector. Okay, so hopefully you're familiar with block diagonal matrices and so on. So now we want to minimize this. Given that we know what A and B are, we derived that. We want to minimize this over the vector space of psi. Okay, so note that this is where the big trick comes in. So note that psi is an eigenvector, right? Which means that alpha psi also minimizes f if psi minimizes f. Okay, and there are obviously many ways to see this. One is you can just do a direct substitution into this, and you'll see that alpha square cancel in the numerator and denominator. Of course, another way to see it is that psi itself is an eigenvector. So essentially, any scalar multiple of the eigenvector is also an eigenvector with the same eigenvalue. So that would also minimize f. And because of this freedom, what you can do is, so we set psi such that the denominator psi transpose B psi is equal to 1. Okay, so we can normalize it. I should say rather than set, we should use the word normalize. Let's see if I can fit it in here. Normalize psi such that psi transpose B psi is equal to 1. So we're picking one of the eigenvectors such that this value is equal to 1. You can always do that, right? You calculate for a given psi what this scalar is, and you just divide by that scalar, right? To get the psi of interest. You can always do that. Okay, so now we're left with what? So we want to minimize this function. We know the denominator is equal to 1. So essentially, it's the same thing as minimizing this, subject to the condition that the denominator is equal to 1. So we've converted this optimization problem into a constrained optimization problem. Okay? So minimizing f is equivalent to minimizing the numerator subject to the denominator being equal to 1. Okay, these two are equivalent conditions now. Okay? Okay. So another way to write this is you want to minimize psi transpose A psi subject to the constraint that psi transpose B psi minus 1 equal to 0. Okay, so this is a constrained optimization problem. Constrained optimization problem. So doing this, essentially the psi that does this satisfies the functional form or minimizes the functional, and that minimizes, that essentially we've shown earlier in the last lecture that that is a solution of the wave equation. That's the psi of interest or the eigenfunction. Okay, so given that we have a constrained optimization problem, we use something called the method of Lagrange multipliers. So I'm not going to explain this technique. I'll leave couple of links in the description on what this is. Essentially, the method of Lagrange multipliers is a technique to solve a constrained optimization problem. It's not very complicated. Essentially, it says that if I have two conditions like this, one condition where I want to minimize this function and I want to do it under the subject to the condition this, then all you need to do is you find the gradient of this function, you find the gradient of this function, and satisfying these two conditions is essentially the same as saying that gradient of this is some scalar value times the gradient of this. Okay, that's what Lagrange multiplier says, and there's a very nice kind of geometrical interpretation to get intuition behind Lagrange multipliers, which I leave a link in the description. You can look at it there if you've never seen Lagrange multipliers before. Okay, so in other words, you start with a Lagrangian, which is, say, the numerator psi minus lambda times the constraint, which is the denominator of psi minus 1. That's the constraint is where you set this to 0. Okay, so this is the Lagrangian, and you take the gradient of this Lagrangian with respect to psi, and you set that to 0. That is the same thing as saying that the gradient of this equal to lambda times the gradient of this. Right? Setting this equal to 0 is identical to this, right? Okay. So, and we set the gradient with respect to psi. L of psi is equal to 0. Okay. All right. So now how do you actually calculate these gradients? So now calculating the gradient of the first term, which is the numerator term, transpose A psi, you can actually show that this is the same thing as 2A times psi. Okay, under the condition that A is a symmetric matrix. Okay, and it is indeed a symmetric matrix because it's a block diagonal matrix, and if you actually go back to each element of A, which is each block of A, where is the function A? Here. Right, replacing I and J doesn't make a difference. It's still symmetric. You can replace these two quantities. Since it's the product of quantities, it is symmetric. So since each block of the block diagonal matrix is symmetric, similarly for this, both A and B are symmetric matrices, right? So why is this the case? So what is this gradient? This gradient, if I expand sort of this, this vector quantity as a double summation, it's nothing but the gradient. So gradient with respect to a vector, you can write like this, right? Ij psi I, let's say Aij psi j. That's exactly what this means. Right? It's the derivative with respect to each value of the vector, right? And that's what gradient is, even in Cartesian coordinates, right? So if you carry out this gradient, of course, you can do it explicitly. You basically take this in, and for every time k fires with I, you get one gradient with respect to I. K fires with j, you get one gradient with respect to j. And that turns out to be summation over I, psi I, mik, plus summation over j, mkj, psi j. Okay? Because when you take derivative, when k is equal to j, then this derivative with respect to this becomes 1, j becomes equal to k, and that gives you this term. In k equal to I, you get this term. Okay? And if I shouldn't say m here, I should say a here. Right? If aik equal to akj, which means it's symmetric, then this is nothing but 2 times summation j akj psi j, which is nothing but 2 times matrix A times vector psi. And that's what we have here. Okay, and similarly, you have gradient with respect to this denominator term is also equal to 2b psi. Right? And this gradient goes to 0 basically. So that's why setting this constant equal to 1, 2, or anything doesn't really matter. Okay, you just need to set some constraint. Okay, so implies that gradient of the Lagrangian with respect to psi equal to 0 is equivalent to writing 2a psi minus lambda to b psi equal to 0. That is identical to a psi equal to lambda b psi. This is the eigenvalue problem. So earlier we wrote these as tildes, so you can put the tilde in if you like, but it doesn't matter. Okay, so what is the value of lambda here? You can actually very easily show that that's nothing but kc squared, because I can just multiply on both sides with psi transpose, right? This also becomes psi transpose b psi, which means lambda is psi transpose a psi over psi transpose b psi. But we know this is nothing but kc squared for the wave function psi, right? Because we know that the value at which this wave function minimizes the functional is kc squared. And that's exactly the Lagrange multiplier. This is called the Lagrange multiplier. Okay, so maybe I should put the box once we do the last part. Okay. So implies that A tilde is equal to kc square, B tilde psi vector. Okay, so that completes the proof. And of course, from this, you can do the connection matrix and then reduce it into the final form, which we discussed earlier. Okay, so this is called the Ritz procedure, or the Rayleigh-Ritz procedure, or the Rayleigh-Ritz method. And it's one of the methods of solving these kind of variational problems to find the fields, right? So this is not the only variational problem. There are many different kinds of variational formulations that you can do in electromagnetism. This is just one of them. And this is what HFSS does to calculate the wave ports. Okay, so the other approach to finite element method, which we won't discuss in much detail, is, but I just wanted to present the general ideas, is Galerkin's method. And Galerkin's method is what is used in HFSS to find, the solution when you do, when you have an air box and you have an excitation, you have an antenna, which is the standard method that HFSS uses. So let's maybe quickly discuss that as well, since we are on the topic of finite element, right? So we'll see why it's called Galerkin. We came across Galerkin once before in the context of method of moments, but it's very, at least the idea behind Galerkin is similar here, although the formulation is quite different. Okay, so this is based on differential equations. So you don't need a variational formulation to do finite element. So if I have a differential equation and I want to solve it numerically, you can use Galerkin's method and finite element. Okay, so we'll treat the general case of a differential equation, which is given by this, where F is the excitation. Right, so this could be wave port, lump port, or some kind of other excitation in HFSS. Right, this is your unknown quantity, usually the electric field. Let's say unknown field. So it could be a vector, it could be scalar. I'm just writing it as phi. and this is your differential operator. We'll see an example of this at the end. We'll see what HFSS uses, but this is just a general differential operator. We're treating the general case, so this could be Helmholtz equation, then it would be the Helmholtz operator, which is delta square minus k square. Then it could be the wave equation, in which case it would be delta square plus d square over dt square. It's an operator, right? So it operates on a function, in this case phi. Okay, so what is the high-level view of finite element method with Galerkins? Is you approximate phi in a function basis. Again, it's the same idea. Okay, so I say phi is approximately equal to summation j equal to 1 to n Cj Vj. Okay, so here Cj are the unknown quantities and Vj are the basis functions. So you pick some basis and you expand your unknown electric field, let's say, in this basis. So of course, this is an electric field and this would be a vector basis, right? If it's a scalar field, then it's a scalar basis. Okay, so obviously this is an approximation because we don't know if this basis is complete. Most likely it's not complete because we are using only a finite number of basis functions. Since we're only using a finite number of basis functions, typically this would not be complete, right? Because the electric field can be pretty large or pretty, not large, I should say, but pretty complicated, right? So in general, it would not be complete, and that's why this is an approximation. Okay. In that case, I will define phi tilde as this exact value. So when I do this summation, I get some quantity which is not exactly phi, it's some other phi tilde. Right? So I can also write this summation as vector v times vector c. Okay. So this vector is different than the basis vector. So if this basis vector is a vector, that would be, I mean, if this function is a vector like an electric field, then this is the electric field vector, whereas this vector is over the index j. Okay, so this is not like a vector, electric field vector. These are column vectors, right? So hopefully that doesn't cause too much confusion, but I'll let you think about that. Okay, then we define, or rather than define, we say that if I substitute this phi tilde now into my operator, and I take minus f, this would not be 0, right? Because since this is not exactly phi, you will have a residual. Okay, so this is called the residual. Yeah, and this residual, of course, is not equal to 0 because phi tilde is not equal to phi. Okay. And now the idea behind finite element is we take a weighted residual Ri. So we weight this residual over the entire domain, omega. So if this is a 3D problem, let's say it's a finite element method in HFSS, the entire domain is your entire air box, right? You weight this residual with some weighting functions. Okay. So these are your weighting functions. So again, very high level view of what's going on. Again, of course, now you want this residual Ri to be 0, right? So if I have n different weighting functions, I have n different Ri's, and that gives us n equations, right? And n unknowns which are the coefficients Cj, which goes from 1 to n. Okay? So this gives you a matrix equation basically, because you have n equations and n unknowns. So let's see how that works out. So before we do that, a special case of this kind of weighted residual method is called Galerkin's method. So similar to how we had in method of moments, Galerkin's method was when the weighting functions and the testing functions are the same. It's the same idea here, where Wi is equal to Vi. That weighting function and the testing function are the same. 1, 2. This is the most popular one, and it's what HFSS also uses. Okay, so if I do this, then my residual function, which is the integral over the entire domain of the weight, which is now equal to Vi, it's the same as Wi, times this operator acting on P tilde, which is V transpose C, minus testing function, basis function Vi. Sorry, no, this is not the basis. This is also the weighting function, Wi, which is now equal to Vi, times d omega, and this must be 0. So this is the set of equations, right? So this corresponds to integral over omega, sigma j. So I'm expanding this now into Vj and Cj. So this is the same thing as sigma j, Vj, Cj, right? So I'm doing that. So I end up with Vi, L of Vj, Cj, d omega, minus integral over omega, Vi, f d omega. This must also be 0. We can pull the summation out and pull Cj out, because the integral is only over Vj. Cj is just a constant, right? Integral applies over V, L of Vj. I'm assuming this is a linear operator. It's a linear, of course, we're only dealing with linear differential equations, which means the Cj can come out. Vj d omega minus, so this is an omega there, omega Vi f d omega. This must be equal to 0. Okay, and this is exactly a matrix equation, right? So this is identical, saying matrix C vector, matrix S, C vector minus B vector equal to 0. Where my S matrix, elements of my S matrix correspond to domain integral Pi LVJ d omega, and my B vector is domain integral Vi f d omega. Okay, and that you can see from these two equations, this equation, right? So this is obviously easy. This is just equal to B. But here we have this quantity, which I can call as, let's say Qi, not Qij, sorry, Sij. That's what I called it. Sij. That's a vector, right? That's a matrix because it's a function of I and j. And obviously computing this depends on what kind of operator, differential operator you have, what kind of basis function you have. And those are the details of finite element implementation. But here I'm just presenting the basic idea. Okay, so we ended up with this matrix equation. We know what B is because it just depends on the source function, which is known, basis function, which is known for a given basis. We know what S is because, again, S depends on the basis functions or the testing functions and the operator, which is also known. So you can calculate all of these quantities either numerically or analytically, and that gives you a matrix equation. And once you have this matrix equation, You want to solve for C. So you want to invert this matrix, right? Or solve this matrix equation, which again is a problem for the linear algebra folks, right? Which is basically MATLAB or Python and so on and so forth. There are many libraries to do this, which of course beyond the scope of this class. Okay, so what does HFSS actually do? Right, so what's the high level overview? First thing is the operator that it uses is the wave equation. Okay, minus omega square epsilon square E is equal to minus J omega J. Let me make some space and write it again. So the operator that it uses, the equation, the differential equation it uses is the wave equation for an inhomogeneous medium. Right, so we saw this equation in class a couple of times, but that was for a homogeneous medium. And this is directly can be derived from, so minus J is the same as I for what we were doing, but in HFSS it's actually minus J. So I'll go back to that. Right, so you have your source function on the left, on the right, and you can't pull this out unless you have an a homogeneous medium. Right, if it's not homogeneous, then this has to stay inside. If you can pull it out, of course, you can take it to this side and then this side, and this becomes your k square and so on. But in an inhomogeneous medium, you can't do that. And HFSS, of course, deals with inhomogeneous media. You have to keep this operator like this. Okay. And the second thing is it uses obviously a vector basis function. Functions with a tetrahedral mesh. Right, so we saw in the 2D problem of waveguide, you use a triangular mesh. A 3D version of that is a tetrahedral mesh. Okay, and these vector basis functions are special. So similar to method of moments, we saw we need vector basis functions in 3D, which were the RWG basis functions, which we didn't talk about the details of. Similarly here, the basis functions are called Nedelec basis functions. And again, we're going to stop it here, not go into these details. But I just wanted to kind of give you an idea of what is going on inside HFSS. Right? So it's not like a complete black box. So today we saw the details of the numerical techniques that HFSS uses. We spent a lot more time in discussing the details of the waveport, how it solves that using finite element, and there it uses this Ritz procedure. And at the end, we also looked at some high-level kind of theoretical developments of the Galerkin's method, which HFSS uses to solve the actual 3D problems, right? So this is the default solution type in HFSS. Okay, and of course, the details are kind of beyond the scope. If you're interested in the details, you can read the book by, I think it's Jian Ming Jing. Actually, I think there's no G here, but there is a G here. Yeah, and this is the finite element methods in electromagnetism. In electromagnetics, I think that's the name of the book. That's sort of the standard book to learn FEM in EM. Okay, so we'll stop this lecture here. Hopefully you found that interesting. Shouldn't erase that. Should erase this. So hopefully you found this lecture interesting. And now you have a better understanding of what's going on internally in HFSS. Okay, so if you have any questions, you can leave them in the comments below. If not, I will see you in the next one. Thank you.